Okay, just to reorient ourselves, remember we're talking about misspecified models. We assume we have a model 1 that just has x1, and we have a model 2 that includes x1 and x2, and we're assuming the setting where we fit model 1, but model 2 is actually true. So we've underfit the model. We've already gone through some results that shows that our beta 1 estimate is going to be biased. However, we will have the right variance. Now let's talk about a third issue, our residual variance. So let's look at expected value under model 2 of n minus p1 s squared, where s squared is the residual variance. Let me write this down here. S squared equals the residual variance estimated under model 1. Okay. Now, in this case, n minus ps squared, we would hope to expect a value to be equal to n minus p1 sigma squared, so that s squared itself was unbiased. Okay, so n minus ps squared, right, is going to be y, I minus the hat matrix with x1, y transpose, times y, where hx1 is equal to x1 transpose x1 transpose x1 inverse x1 transpose. Okay, so recall our formula for the expected value of quadratic forms. That's going to be the expected value, the part that we want, which is the expected value of y transpose I minus h of x1 expected value of y. So recall that we're assuming model 2, so the expected value of y is x1 beta 1 plus x2 beta 2, then transpose I minus h of x1, and then x1 beta 1 plus x2 beta 2. Okay, so there's that part. And then there's the trace of the middle part times the variance of y. So that's the trace of the middle part, which is I minus hx1, and then times the variance of y, which is sigma squared times I. I'm just going to omit the I. Okay, now let's garbage collect here a little bit. Now recall I minus the hat matrix for x1 times x1 and x1 transpose times I minus the hat matrix for x1. Both these are going to be equal to 0. Okay, so I can just get rid of that term and get rid of this term and say that this is beta 2 transpose x2 transpose I minus hx1 x2 beta 2. Okay, and then trace of I minus hx1 sigma squared. We've done these kind of calculations before. The sigma squared pulls out, and trace of I minus hx1 is n minus p1. Again, we did that exact calculation when we showed that the variance was unbiased and we went over expected values of quadratic forms. Okay, so what we're seeing is that the expected value of n minus p1 times s squared works out to be not n minus p1 times sigma squared, this part. It has a bias. And this bias is strictly positive, right? It's a positive definite matrix, or it's non-negative at least. It's a non-negative definite matrix, then times beta 2, a quadratic form with beta 2 on the outside. Okay, so that point, that term right there tells us that we're likely underestimating the variance. I'm sorry, that we're likely overestimating the variance. Okay, and that makes sense. What has happened in this case is we have included variance into residual variance that's actually systematic variance. So recall the true model was y equal to x1 beta 1 plus x2 beta 2 plus error. And we've just fit that part. So our model treated the x2 beta 2 like it was error. So it got that extra variance got thrown into the residual variance, okay? And what gets thrown into the residual variance? Well, x2 I minus h1 x2, right? That is basically x2 with the residuals having removed all the linear associations with x1. So it's basically the residual variance of whatever x2 explains in y, treated as if it's part of the residual error term, all thrown together. Okay, so it makes a lot of sense, the bias that we get. Basically, the bias says, you pretended like these variables weren't important, so I put that variability into my residual variance, and then my residual variance estimate is then biased upward. Okay? In addition, my residual variance in this case is not going to be chi-squared. When I divide this by sigma squared, it's not going to be chi-squared distributed. It's going to be non-central chi-squared distributed. Okay? I'm not going to go through that because I don't want to have to introduce the non-central chi-squared distribution, but this just also reminds us that this model, the residual variance under an underfit model, is not going to be chi-squared distributed. Okay, now we've gone over a lot of the impacts of underfitting, in which we saw some important aspects of bias. Now let's see what are the consequences for overfitting, because surely the answer to underfitting can't be throw every possible regressor into the model to avoid underfitting. There has to be some penalty to including variables in the model that we shouldn't include. So we've already seen that the most likely penalty for excluding variables that we should have included underfitting the model is going to manifest itself in bias in the residual variance estimate and bias in our effect estimates. Now let's see what goes on when we actually overfit.